simplify life with dependent types by introducing dynamic equality. Please go ahead.
Yes, hello. My name is Try. Hello? Okay, cool. My name's still Mark Lemay. You may recognize some of these people from the last presentation, so this may be a little bit worse. We'll see. Why would you want to do this? Well, dependent types are great. You can specify really important invariants you as the programmer want, and you can keep index out of bounds from happening. Here's a little program in Agda. Hopefully you can kind of read it. And it repeats a number. It repeats, it makes a length index list of trues if you give it a number of that length. If you give it a number and give it a list of one more than that length, it'll give you the first thing of that list, and we know because of the type that it can't look at an empty list and get ahead. And you can build it all into one little program, and this is great. Unless you typed it in slightly wrong, in which case it doesn't work at all. So, when you hit a problem like this in Agda or some other system, usually you get an error. You can't get any type information out of the system. You can't use the REPL. You can't continue using the file and add things to the program you've already written. And this is because in these systems, generally speaking, the 1 plus x and x plus 1 are not definitionally equal. So how should you handle definitional equalities during runtime, type checking? A lot of people have a lot of good answers to this question, but I think we're asking sort of the wrong question. So why would we want to do this at type checking at all? Type checking generally needs to be extremely fast for programmers to be happy with it. Our equalities are almost always going to be undecidable. It's just a recipe for misery, basically. So for this talk, we're going to suggest, instead of trying to deal with this at compile time or type checking time, why not warn with the same information you would get at the traditionally, and just put checks in when you need it so that if it pumps into something at runtime, you get a runtime error, possibly with the exact witness of inequality that shows you were wrong and a pointer to the warning that you should have listened to in the first place. So if I can get you to buy in, at least for the rest of this talk, that this is something worth doing, let me explain roughly how we did it. So we have sort of a standard architecture where we have a surface language, an elaboration procedure, and a cast language. And just so we're all syntactically on the same page, let's look at what the surface language consists of. It was designed to be kind of as inoffensive and minimal as possible. We have just barely the stuff we need to get by. It is type sound. You can have a bidirectional type system for it. And it's logically unsound, and let's just say that's for convenience for us. The real meat of the work happens in the cast language, which is almost the same as the surface language, except that we've removed the type annotation, we've added an explicit casting operator, and we have an assertion operator. So if you want to use, it's best to see it as an example, if you want to use 7 in a place that would want a bool, you would write something out like this, where 7, it has type nat, we want to use it as type bool, we know that those two things are the same type, and we have a location to this, the static place that asserts it, and we have an observation that'll evolve and give us the observations we need to track the error, if it does turn out to be an erroneous equality. Now, just for the sake of this talk, we're not going to be dealing with all of the bookkeeping, or it makes it hard to deal with all the bookkeeping if we put all this stuff in. So we're just going to abbreviate these things and ignore the type stuff, and ignore the location and the observation, and just assume that those are always going and keeping track of things correctly in the background. Yeah, so that seems like it might work by itself, but there are a couple things we had to do to make this actually work. So here are the sort of technical highlights. Casts and asserts can work their way into type signatures. So that's not good. To deal with that, we actually separated out reduction and blame. So this is a really convenient. There's other work that mixes dependent types and errors, and it's so convenient not to have to deal with that. So we just say this term gets stuck as far as reduction is concerned, and blame can be extracted as far as the blame judgment is concerned. Casts can block function application. And if you're familiar with contracts or gradual typing or anything like that, you'll probably see straight to the answer. But we just need to add the reductions that make us be able to apply things to casts and just do the bookkeeping you need to push things around. Finally, we have some kind of question about how we would keep track of types and equality within the cast system. So if we have some kind, this is a pretty contrived thing, but hopefully you can get what's going on here. If someone asserts and at is the same, and someone, add and at is the same, and someone gives it the inputs, where they're asserting 1 and false is the same, and true and 2 is the same, well, what type should this have? Should it be nat? Should it be bool? Should it be both? Should it be neither? How should this be considered equal? Should it be equivalent in some sense to 3 or equivalent in some sense to false? Well, we extend the typing relation to this thing we call endpoints, and it lets us keep track of the interpretation of every term in a type-consistent way. So we'll say that this both has an endpoint where it's add 1, 2 at nat, which is in some sense the same as 3, and it also has an endpoint in and false true at bool, which in some sense is the same as false. And we're not going to talk more about these things. We're just going to pretend typing works regularly from here on out. Yeah, and we can kind of, we've extended our own kind of terminology for this. So instead of saying well typed, we'll say well cast, and we'll say things are well cast when the endpoints are good. And that leads us to our top level theorem of this, which instead of type soundness, we call cast soundness. And instead of type soundness where well-typed terms don't go wrong or don't get stuck, we're going to say well-cast terms don't get stuck without blame. And the proof sort of goes along similarly to the progress and preservation proof of type soundness. Okay, now let's take a look at the elaboration procedure. And we're going to take a real distant view of this. The elaboration is basically just bidirectional type checking. We're going to just do the normal bidirectional type checking stuff, except when we would run terms to figure out when they're equal. We're just going to slap a runtime check there. And in practice, we might do a little bit of courtesy evaluation just so things don't get too messy. And this gives it a very different character than gradual typing systems. So where a gradual typing system would want to handle every untyped piece of syntax, we can handle a lot of nonsensical syntax, but not things where we don't know what the user intends to type it. So for instance, if someone has a function from bool to nat, we can give it 7 and it'll put the checks in the right place and everything will be okay. If someone just says lambda x arrow x, well, it's not going to know what type you intended x to be, so it won't elaborate that term. So that's the functional fragment of this. And we can do a quick example of the first thing we did, which is this silly little function. And the way you get the warnings is you just read off the assertions, and you get nice little error messages, or warning messages. Now, I think it might be good to break for 1 or 2 questions, just because that was a lot, if that's okay, before I continue with the rest of the stuff. If anyone has questions, that is.
That's fine.
Yeah.
Yeah, so I'm really curious about how the elaboration works. In dependently typed languages, generally there's meta variables are used to fill in implicit parameters and so on.
We're not doing that right now. Good question.
Right, okay. So, yeah, okay. So, yeah, I was going to ask how you choose between filling in a meta variable or inserting a cast. And if you don't have meta variables, it's an easy choice.
Yeah. I have some thoughts on how you would do it, but we're not doing it right now.
Cool. Thanks.
Yeah.
I was just curious if every equality becomes a cast, or if you can.
So if there's something obvious, just for sanity's sake, we kind of, if 1 equals 1 is an assertion, we're just going to say that's fine, right? So it's kind of a heuristic thing with a limit, but so not every equality will become a cast, but we set up the theory so that every equality sort of becomes a cast. But there are some exceptions to that, but yeah.
I just have a kind of high-level question. So I know there's been a bunch of recent work on gradual dependent types, and this looks, both the language and the elaboration, the setup looks very similar. And I was wondering if you can contextualize this for me. So I know, for example, there's different design space about whether you maintain soundness or normalization, and some different choices.
Yeah, so this actually awkwardly doesn't fit well into a gradual typing framework. And that's, well, so the work on gradual typing and dependent types is pretty interesting, but it's pretty complicated. It involves changing like surface level syntax, which is not something we want to do. Though I think maybe you could say we're just gradually typing the equality relation. To the extent that that would ever make sense, I don't, yeah. Okay, so that was the easy story of just functions without data. But we also handle data and pattern matching, and that requires a lot of additional machinery that I'm going to quickly run through the high points of. So just to make sure we're syntactically on the same page, again, here's the surface language, here's the data definition of that, and the data definition of a length index list called fect. And here is the function that will take a number and repeat it, and repeat something that number of times. And we're using explicit case expressions, which are made up of a scrutiny, branches, each branch has a pattern, each branch has a body, and there's a motive that's written out here in maybe a slightly different syntax than people are used to seeing, which tells how the branches type check in the context of the pattern. And in real life, mostly the motive can be inferred. Okay, so the surface language data works okay, but when you extend the elaboration in the cast language to handle data, you have to handle a lot of things. First of all, or two specific related things. Normal forms don't match patterns anymore. So that's not good. And also, we're using the full kind of range of pattern matching with unification to resolve things, so we have to handle unification as well. So first of all, the pattern matching syntax only makes sense because you have a head constructor, and when you have a normal form, you expect the head constructor to be there and it links to the pattern. In the cast language, that's not what happens. You could have 0 or more casts blocking that constructor. So we're going to add a bunch of machinery that says we can always insert a vacuous cast, we can always bunch up casts together, and then we can say every data constructor has exactly one cast on top of it that we can then include in our pattern syntax. Then we need to deal with unification. And the way we're going to deal with unification is by recording the normal steps you would use to unify into the terms. And this is so we can redirect blame to the thing that caused it. So this is probably only explainable at this point through an example. Here is an expression that'll take the head of a term. And we're just going to speed past this because I think we're running out of time. So to elaborate this, we're going to take the regular constructor, or we're going to take the regular pattern, we're going to insert a bunch of cast variables that will pick up the cast that will be on this in the cast language. Then we'll take the body and we'll prepare it to accept a bunch of casts that will be solved through unification. And then remember, unification is saying, well, this little a is of type big A, and we know the type of this whole cons expression is going to be that thing, and that thing we know from the motive is going to make that a bool, so we have big A equals bool, and we can say little a is of type bool. So we have the same equality that we're capturing from the cast, and we're going to inspect it. We're going to add some machinery to inspect it, and then we're going to say we know A is of type bool according to this input we got. Then also for pattern matching, the system will synthesize the constructors that aren't there, and then use unification to show that they're possible. For our case, it's very well possible that a constructor might show up under a bad cast, so we need to handle it. So we'll capture that. We'll add syntax that allows us to witness a direct inequality. And and that will let us redirect blame. So the important thing to notice about this elaborated term is that we haven't inserted any of those squiggly assertions. So there will be no warnings from this code, and there can be no blame from this code. Any blame will have to come from the input. I don't think we have time for the next thing, so I'm going to run to the end. Just a quick overview of our results. We have a cock proof due to Robin, who's just did the last presentation, of an old similar system. We haven't gotten it for the new system because we don't have the patience, or I don't have the patience for it. Without data, everything works out pretty cleanly. With data, everything is kind of, we assume it's right, but it's very complicated to try to like formalize anything. In the future work, there's a lot of, we actually have an implementation you can try, and we're so close to getting a web UI working. I was hoping we could get it this weekend, but if you're interested, I can tell you when it's done, maybe next week. There's a lot more things in this philosophy I would like to investigate, where we just do fewer errors and we do more warnings. And we're actually in a very convenient place if we ever could get a user study together, because we have a language that's exactly the old way and a language that's exactly the new way, and they're exactly the same except for that one thing. Well, thanks. If we have time for any more questions.
Yes, we still have 2 full minutes for questions.
And I'll be a little crazy. If you're watching this in the future from recording, email me if you have questions.
So I'm a little confused by something you said. So to an earlier question, you said like no unification is being used, and then in the
no meta variable unification. So we don't have implicit arguments.
Okay, but aren't you introducing implicit meta variables in your elaboration?
Yes. Sorry. So there are multiple places you would use unification in a dependently typed language. We're using it in the place that is involved in pattern matching. We're not using the feature of implicit arguments or meta variables in the kind of surface syntax.
Okay, thanks.
Yeah. Thanks for clarifying.
So no more question.
Oh my god, my mind's gone blank. Sorry. I had that question in my head and it's super embarrassing. I'm sorry. I'll retract it and then ask you afterwards when it returns to me. Sorry.
Yes.
Okay, so we thank the speaker again.
Okay.